Swayam Prabha. Digital India. Educated India.
Energy Day discussions will continue. So the last presentation you all listened to a great talk on an overview of the energy sources, right? Different types of energy sources and how different it is in different parts of the world, okay, and even within a state, what is happening. And I think there's a lot of information out there, India related information, which you can go and know about your own region, okay, to understand it better. So now we have another interesting talk. It's going to be on the use side of it, right? The one is the supply side of it, what we listen to mostly, and then in the use side of it also we can make a lot of interventions and make it more efficient, and that is even more sustainable strategy than trying to augment whatever the demand is, right, with more and more power. Can we cut down, okay, and what is the energy use efficiency in different sectors, industry or even campuses like this, okay, in the transportation sector, every sector we can work on the use, improving the use efficiency, okay. And industrial energy assessment cell was formed in IIT Madras probably about 6 years ago, right, to 7 years ago. 7 years ago, we realized that there is a potential here and it needs to be the awareness needs to be created first of all, and actual projects needs to be done industries and other campuses. So Professor Mahesh Panchagla and Satya Sheshadri from IIT Madras Applied Mechanics Department, they initiated this process, and now it has grown to more than 6 to 7 IITs. We are trying to set up these cells, and they are working on different projects, right? So today we wanted them to give an overview of why is it important in the energy assessments, and some of the projects what they have done and their outcomes in the context of sustainability, what we have been talking about all along.
Thank you for having us here. I'm Swarnapriya, and I'm the project manager in IEAC. And along with me, I have two colleagues from the technical team, Seeteshwar and Karteshwar. So what we'll be taking you through for the next 1 hour is more about IEAC. Please get used to this acronym. You'll be hearing it a lot over the next 60 minutes. So it stands for IEAC, Industrial Energy Assessment Cell. It started off as a dedicated cell back in 2018 within IIT Madras. And it was like the energy pillar for CTAP, which is the Center for Technology and Policy within IIT Madras. And right now we have close to 10 centers as 2025 across the country, expanded as IEAC throughout here. And this is a bit of a journey that we've had over the last 7 years, where you see by the time we reached 2022, that was when the IEAC became a CSR initiative of Kotak, and looking at all the potential opportunities that are there and the industries that we can cater to in terms of, say, energy efficiency. More IITs joined us. It was about 4 IITs that joined us in 2022. And then by the time we went to the next year, another 3 more. And as of 2025, we have about 10 centers across the country. And a couple of milestones that you see here across are we have crossed more than 320 energy audits as of now. And I hope I'm audible. And yeah. So about 320 plus audit and covering more than 30 plus sectors across the country. So I think this is the framework of our entire audit process that we do. So it's split into three phases. One is the pre-assessment phase, next is the assessment phase, and then the post-assessment phase. So what happens in the pre-assessment phase is we start off with data collection. This is even prior to visiting, say, the industrial facility. So, a pre-questionnaire is sent out to the clients where we collect data like, say, what is the type of industry, the kind of major utilities that are there, the connected load, and the plant operating conditions, and so on. So that will give us an idea as to a rough estimate of how much time it would take for the audit and to get to know or familiarize ourselves with the utilities that are there. And then comes the walkthrough audit. So what happens in the walkthrough audit is uh, we basically validate the data that we've received. So a couple of our auditors, along with, say, their, it can be the operations manager of the plant and so on, we take a walkthrough across the audit and validate the data that we've received. So to see how the production processes are and to see any, inefficiencies that are that we can spot very easily, and also for some operational issues. So that is what happens in a walkthrough audit. And depending on the size of the plant or the industry, it can take anywhere about 1 or 2 days to do this. And then third phase is the measurement planning. So based on the number of utilities that are there, and it can be like X number of furnaces, so many number of boilers, and so on, we'll have to plan for the measurements. So uh, and I think every important parameter needs to be monitored. So we plan for it, and there's a lot of switching on and off involved in this process. So it shouldn't also affect the schedule of the plant that is there. So that is when the measurement planning happens. And moving on to the assessment phase itself, that is where the detailed energy audit comes in, where our team of auditors, they go to the plant and do an in-depth analysis of all of the facilities energy systems. So we have a lot of instruments like power quality analyzer, it can be a flow meter, and so on, and to measure, say, the different measurements, and we collect very precise data. So this is a very critical step of the audit process itself. And then we collect all of the data, and a performance analysis happens. So anywhere between 40 to 50 parameters we receive from the different instruments that we analyze, and we closely monitor 10 key parameters, like it can be the harmonics, the the kilowatts, the transformer losses, and power factor, and so on. And then once this performance analysis is done, we have a closure meeting with the client. So where we present the initial findings from our performance analysis. So we say that there is a potential of so many number of energy conservation measures that is possible that you can adapt to improve your energy savings and become more energy efficient. So once this meeting is done, that is when we come back from the facility and then do a very thorough data analysis and prepare a detailed project report. So, and where the key findings, so it'll be in terms of say ECMs, which is the energy conservation method measures that are possible, say, for this particular facility, along with, say, the ROI for it, and potentially the savings that we can have from it. And the last phase is the implementation phase. So once we hand over the report, that's when the client decides to adapt and implement a couple of these measures. So, which is, I think, not just for us, but across the energy auditing industry, it's a challenge when it comes to the implementation of it for various reasons. So, and one other milestone that we've had in 2024 was the development of an in-house audit tool. So it started off with the idea to digitize the energy audit process itself. And this is a tool that we've developed, and I would say it is still a work in progress because right now we've been using it and testing it on a couple of energy audits, and we see a lot of potential in it. And the plan is to also expand it using AI and IoT and to entirely digitize it and also become a database, not just for IEAC, but also for, see, the entire energy industry of our country. So that's with the tool. And yeah, this is just say a screenshot of the component dashboard that we have in the tool. So apart from the ease of use, I think it's also a lot more time saving when it comes to drafting the detailed project report for the clients. And I think I spoke about the energy conservation measures, and they are categorized into two types predominantly. One is on the payback and in monetary savings. So where there are three variants, and one being a very low hanging investment, that is something that can be implemented with almost zero cost. An example would be like leakages, which can be sealed with a sealant, which is, when compared to the ROIs or the efficiency itself, it's very, very small. So there are ones that have a payback in less than 3 months, and then the mid range, which is anywhere between 3 months to 2 years, and the one above 2 years. So this is one type of ECM categorization that we do. And another is on the basis of the operational methodology and also the types of energy efficient technologies that you can use. So on the right, if you see, there are examples like installation of a heat pump in a boiler. That is one way where you can improve efficiency. And then there is the electronically commutated fans that can replace the belt driven fans, and also the screw blower replacing the twin lobe blower. These are some of the energy efficient technologies that the client can adapt when it comes to improving. And in addition to this, we also customize, say, the solutions based on the site conditions for the clients. And this slide talks about, say, the overall outcomes across, say, the 10 centers that we have. We have like close to 320 plus assessments that have happened so far, with almost close to 3,500 recommendations and 30 plus sectors. So you have anything from FMCG, textile, and so on till I think aluminum die casting and everything else. So, and here it shows the recommended savings that are there and the annual cost savings that is proportional to it. And then last row shows the implemented energy savings and the cost savings for the project. And apart from doing energy audit itself, our team also do the greenhouse gas assessment. So what you see to the right is the GHG emission reduction and the one that we were able to achieve. And this is just a couple of industry standard equipments that we use to carry out our energy audit process. Yeah, these are our partners who we collaborate with frequently, especially the Bureau of Energy Efficiency, who usually dictate the standards that we have to maintain for, say, the specific energy consumption and so on. And we also work closely with them in the Aditi scheme that was rolled out recently, and also for the PAT cycle for designated consumers, basically from the energy intensive sectors. And then what you see here are some of the key clients of IEAC. So you have pretty much a very diverse set of sectors that we cover. And here are some pictures from one of our audits for Ariagro tea factories. And I think now I would like to hand it over to Siteshwar, who's our energy assessment engineer, to take you through a couple of interesting case studies from 3 of our sectors.
Myself, I'm Sedishwar. I'm an energy assessment engineer. I've been involved in this energy field for almost 2.5 to 3 years now. We have been part of few energy audits. I'm just here to share what I have observed over these years and what are all the ground realities which we face in the industries. So, as Indu ma'am had nicely pointed out, that we will be focusing on the use side of the energy. So we have, I think you would have gone through the generation side. So we will be focusing on what is the use side and how we can efficiently optimize it so that we can conserve energy and we can, so what is energy save is energy generated. So how efficiently we can conserve it. So in India, almost 42% of our energy consumption is around in the industries. So the industry sector itself contributes to around 42% of the national energy consumption, and followed by the other sectors, which is under transport and other textile sectors. And what are the other sectors we'll be classifying will go on the other half. So roughly we can say half of our energy consumption is in the industries, be it manufacturing industries, food processing industries. So we can list it down, and if you combine everything, it's almost 42% of our energy consumption. So what are all the types of energies we will be using? The is one major question. So electricity is one form of energy, and fuels like biomass, coal, and furnace oils. So these are some other fuels. An industrial sector such as manufacturing sector or a food processing sector will be consuming. So today we will be delving into how there are, you can classify again the industries, industrial energy consumption into two parts, like the energy consumed in a process and the energy consumed the utilities which are aiding the process. So there is a main process line which is producing the product, and there is an aiding utility. The aiding utility is consuming energy for producing this product. So we will be focusing only on the aiding utilities. We will not touch into the processes. Processes is the advanced level of energy consumption. So if when we intervene into the process of an industry, we are intervening into their core part of the operations. So that will be in the next level. So initially we will go into the utilities, and we will assess what are all the efficient means we can reduce our energy consumption, and what are all the measures we can provide them so that they can use their energy efficiently. So it can be as simple as switching off some unwanted pump, or it can, we can just say you can close this valve, or you can change the pressure setting of this. So these, from starting from these simple measures to adding an one more advanced technology, you can automate your in a process using a feedback control from the product. So it can be as simple as this, or as investment heavy products, we can also classify it as the classify as these above mentioned for things. So these are the few utilities which I have covered. So this actually we have more than this. We can consolidate it around to more than 20 or 25 plus utilities. But for the sake of the time and time constraint, and we have only 30 minutes of this 30 to 35 minutes, I have consolidated for these utilities. So these utilities is majorly used in the industries, it be it a manufacturing or food processing. The utilities which used are air compressors. Simply they just take the ambient air, increase the pressure, and we will use it for various applications such as packaging. You have seen packaged food materials which have sealed inside, it is having nitrogen and some kind of things. And to move a simple piston arrangement in industry, an equipment will use air. So these are the few places where air plays a major role, compressed air. So that is the first utility, and the next, boiler is widely people would have known boiler. And the third one is chiller. Chiller is simply chilling for, it can be for air or it can be for water. So for simply chilling the air or water, we use the chiller. And transformer is predominantly present in all the industries. Since you are supplying power from a substation, you have to receive it in a through a transformer, you have to step it down, then you have to use it in your industry. Then you have humidification plants. These are mainly used in textile industries. So humidification plants, they maintain the humidity and the temperature of an environment. So inside a textile sector, you need the humidity and the temperature plays a major role in threading. So you have to we will see in detail so how in textile sector these processes are going on. For that, humidification plants are necessary. And we have AWS, which is automatic waste evacuation system. So this is again inside a textile industry. So in the textile industry, you will have waste evacuation suction systems. So for that, we have AWS and we have CIP in the last. CIP is cleaning in place. Cleaning in place is majorly used in pharmaceuticals and dairy productions. Since wherever you need a food grade product, which is going to be consumed by a individual, you will have cleaning in place. Since the process needs a certain level of contamination free environment, we will use clean in place. So we will go in detail by in each one of these utilities. So before diving into the session, I wanted to share few of my perspectives about the life cycle assessment. If we need to conserve energy, or if we need to uh, do something in a process, we need to first model the process. So if you model the process, only then you will know where is the point which we can focus on and where we can conserve conserve the energy. For example, if I'm receiving a said amount of 50,000 in my account and I'm spending 30,000, so remaining 20,000 I have saved. So I have a scale of 20,000, so that I can say I have saved 20,000. So in the same way, if we need to quantify what we are saving, if we need to know and how to save, we need to model the system first. So life cycle assessment will provide you that overview of how we can model the system and where we can focus on, so that you can reduce the energy consumption. So life cycle assessment mostly whatever operations we are performing as a human being, whatever human intervention we are doing to a process, will quantify and we will quantify it. Let's say we can simply we are just riding a bike, or we are just drinking milk. So these things we will just quantify on how much energy you are consuming in just riding a bike. You have rode a bike for, let's say, 20 minutes for this long stretch, then you have consumed this much of energy. That is a simple action for us, but it has generated so much of, you have consumed so much of energy, and you have emitted corresponding emissions because of that simple action. So from a simple drinking of milk to driving a bike, we can model the system and we can focus it. So first example which I have included here is from a dairy industry. So for producing 1 carton of milk, they have consumed around 0.76 kg of CO2. So just producing 1 carton of milk, which is 1 kg of milk, which we are consuming daily from the farm, from the animal to the consumer. So we have emitted around 0.76 kg of carbon dioxide. So we are again classifying that 0.76 kg. Like, what are all the parts which we have classified that? So first, in palms, it is around 0.32 kg of CO2. So let it be in the manure or the equipments which are used in milking, the energy consumed in the milking equipments. So in farming, there are many uh, pesticides and insecticides where you will be that those pesticides will be emitting uh, gases, which is GHG gases. So we are accounting those gases, and if we quantify it, it is coming around the average of 0.32 kg of CO2 in the farming. And next we are moving to the manufacturing sector. In manufacturing sector, for a dairy plant, so for in homes, how we boil the milk, the similar kind of process is happening there, like pasteurization, homogenization, and we'll be then packaging all these materials. So mainly it involves pasteurization and homogenization. So for the process of receiving the milk in an industry, then you will be storing it in tankers or silos, then you will be pasteurizing it, then you will be homogenizing it, then you will be packing it, and these things happen in a day-to-day basis. So these are very highly energy intensive industries. We might think that simple milk is like we are consuming it daily, but this is a very high energy intensive sector in India. Recently, Bureau of Energy Efficiency has classified milk as dairy industry as a designated consumer. Designated consumer in their eyes means they are consuming a more energy after a threshold. So let's say 25,000 TOE. So Bureau of Energy Efficiency mentioned that if your dairy industry is consuming more than 25,000 TOE, 25,000, I might be wrong, I think it's 2,500 or 25,000. It is TOE, it is a ton of oil equivalents. So if the industry is above that level, you are classified as a designated consumer. So that's what I just wanted to know. I just wanted to say that even a simple manufacturing sector like a dairy is highly energy intensive. And after that you have cold chain. Cold chain is that we just don't have milk. We have butter, we have ice creams, and we have many other products from dairy as a byproducts. So these products need to be stored. These products need to be transported. So to store them, you have a environment conditioned room, which is having a set temperature of, let's say, minus 15 degrees Celsius. Mostly for ice cream storages, they'll have around minus 28 degree Celsius, and these temperatures need very high energy intensive utilities. These utilities will consume more energy than the production itself. So these chilling parts inside a dairy industry will consume more energy, more than the pasteurization and the homogenization. So your main process doesn't take much of your energy, but the storage, the transportation, and the environment around it will consume more energy. So these cold chain contributes to around 0.22 kg of CO2. And finally, the consumption. You know the consumption use. So what we do in our daily household, we will just store it in a refrigerator, and these refrigerators have CFCs, and these CFCs will be emitted. So these CFCs and the electrical energy consumed for a refrigerator, so these all other things combined, what I said is just an example. So these all combined, we have 0.1 kg. So overall, for just 1 kg of milk, around 0.76 kg of CO2 has been emitted. So here, where industrial energy assessment cell, what is their part in this whole process in LCA? We are coming only in the manufacturing process. So in the manufacturing process, what are all the processes involved? What are all the aiding utilities for the process? We are focusing majorly on the manufacturing part of this LCA. So energy consumption, in other words, you can say emissions. So consumption you can correlate with emissions also. So if you are consuming this much energy, you are emitting this much CO2. So you can directly relate these two. So these emissions have been classified into 3 types, so that it is easier to quantify all these emissions, and so that you don't have overlapping of emissions. So say one person is saying I have done this and I have emitted this much, and say one more person is saying I have done this activity and I have emitted this much. So how we will quantify them? We need to quantify them in a list, since this is a overall national wide and worldwide factor. We have to quantify these types of emissions into 3 categories. So whatever emissions which we are which is inside the premises. For example, we can say scope 1 direct emissions. Inside an industry, if you are burning fuel, or if you are doing an activity which is inside your premises and which is emitting directly, it is coming under scope 1 emissions. And scope 2 emissions is purchased energy, or for example, we can say electricity. So electricity, the emissions is caused in the generation side itself. So in the generation side, you have burnt coal or burnt some fossil fuel or some fuel, and you have emitted the gases, and you have produced the electricity. But the end consumer is inside the industry. The industry is not emitting anything, but the generation side has emitted it already. So these things come under scope 2. So these are indirect emissions. You are the user of the energy, but you are not emitting it. So these are at scope 2 emissions. And scope 3 is the value chain emissions, which is transportation, distribution, and products. So whatever I had taken for dairy, like after production of the product, you are transporting it to one place. So these things will not come under scope 1 or scope 2. These things come under scope 3 activities. So in assessments, we directly focus on scope 1 and scope 2 emissions. So we will focus what are all the energy use inside the premises, what is the scope 1 emission of the premises, and what are all the scope 2 emissions of the premises. So initially, we can start with the air compressor. In air compressor, there are many types. If we delve into the technicalities of it, there are many types in reciprocating. We have screw compressors and we have centrifugal also. But we will for the major classification which we have observed in the industries are mostly reciprocating and screw type. For a common day-to-day example, if we go in the petrol bunks or stations, we will get compressed air for our tires, like for two-wheelers and four-wheelers. So there you can see an reciprocating compressor in the corners of the bunks. So that is an example for a reciprocating compressor. So this is a very small, the day-to-day example is like a very small reciprocating, but in industries you will have a room full of compressors, like they need nearly 75 kilowatt or 100 kilowatt or 125 kilowatt capacities of. They'll have some dedicated space, nearly like 3 to 4 large screw compressors will be there, so that they can provide compressed air for the whole industry. So major energy conservation point which we had observed in the compressed air facilities are the leakages. Simply like when there is compressed air, if you compress air to a certain extent, its pressure increases, its temperature increases, and if when this flows through a pipeline, your pipeline is having a border of, you are having a high pressure air and you are having ambient air. So the air tries to escape. So you have many leakages at many points inside a compressed air system. This might sound simple, like you are compressing air and you are transferring it, but it is leaking. So just look at the savings in electrical at the final point. You have 3,08,937 units, which is contributing to around 30 lakhs. So around 30 lakhs of your energy is simply wasted just because of the leakages present in the compressed air lines. So we are there to just portray these values to the industry. So when you put the values, instead of saying go and arrest your leakages, they might listen, they might understand, but instead of that, you are saying the savings in terms of electrical energy and monetary values. So in terms of electrical energy, around 3 lakhs of units is being wasted because of this. Is an actual case study which we had performed in an industry. So we are saving around 30 lakhs of monetary savings through this energy conservation measure. This we had presented to the presented to the management in a closure meeting, and they had taken it up, and they will, so in terms of leakages, they will then and there start arresting the leakages, because it is very simple. So they just have to arrest the wherever leakage points are there, they have to arrest it. So this is an optimizing unloading hours. So for this, we can say an example of, we are riding a bike and we just leave the accelerator, and for few yards or few kilometers, the bike will not stop. It will be going on a free run. So but the engine is still on, the fuel is being consumed, but the bike is still moving. So that case is for the air compressors also. When there is no use for air compressors, the air compressors will be running ideally. So this ideal running hours should be reduced. This ideal running hours we need to calculate, and we need to optimize this as much as possible, so that only when it is necessary you will turn on the compressors. So by optimizing this unloading hours, so we will be saving around 15 lakhs of rupees and around 1.7 lakh units per annum. So this how we will save will be the next question. So we know when the compressor is not running, I mean when there is no demand, a compressor is still running, but how we will save it? There is one thing called variable frequency drive. We have VFDs. These VFDs we can install for these compressor motors, and this VFDs will provide the right amount of speed for the motors so that it will deliver only the required amount of power, and only when the demand meets the motor will be running. So by this technology, we can save around 15 lakh rupees and 1.7 units per annum. So this is one of the classic example, like simply by just changing a pressure setting in your compressor, you will just have to go into the settings and you will just have to change it. This mostly happens in industries due to lack of awareness. So when they receive a compressor, the industrial person, what he does, he will install it and he will automatically configure it for whatever settings he knows. So he is not quantifying what is the amount of pressure needed, what is the amount of CFM needed. He will just install it, and the pressure setting usually it is higher than what is required. It is around 8.3 to 8.3 bar. So but the 8.3 bar is not necessary for their operations. Only 6.5 to 7 bar is sufficient. So these guidelines we will be referring to Bureau of Energy Efficiency. So Bureau of Energy Efficiency has a separate set of guidelines for each utility. So if you are having this utility, it should operate under these parameters. Only then you are operating it efficiently. So just by changing this pressure setting, they can save around 3 lakhs. So this one is a very classic example of just being aware of what they are doing. This is just a basic everyday practice, so that to check whatever pressure setting is there in your compressor, is it necessary or is it more than necessary. So these kind of things also we will be observing. So next up is cooling tower. Cooling tower is simply, you would have observed if you come to I think research park or somewhere, or in larger buildings in AHUs, you will have a larger tower from where water is falling and hot air is being sucked out. So these cooling towers are primarily used for chillers, and these are the condensers for the chillers. So in a milk powder plant, this cooling tower, we had two cooling towers which was operating for the milk powder plant. So in milk powder plant, in terms of in simple terms, we can say milk is being condensed, and it is again it is passed through a high pressure nozzle and it is being converted to powder. So for condensing it and for other processes, you will have many utilities, and one such is the cooling towers will be there in the aiding part of the milk powder production. And in this part you have two cooling towers. Simply we will just calculate what is the required amount of heat load is necessary for them. So if the heat load is not matching the product, let's say only one cooling tower is sufficient for the heat load, but they will be operating two cooling towers, because there is no visible value saying that this much amount of heat load is there, this much amount of heat load is required. So they will be operating two cooling towers because there is no such intimations. So we will be assessing the utility and we will be calculating the heat load, and we will just say you can just switch off one cooling tower and run with the other cooling tower. Only one is sufficient for you, and you can your process is happening smoothly, and there is energy conservation in that also. So this around this the similar principle for the two cooling tower setup is happening in this also. In the cooling tower, you will have a pump which is used for circulation of water. So usually they will give one pump for running and the other pump for standby, but some people will run both the pumps. So when they are not aware of the situation, they will just run both the pumps, and both the pumps are not needed for just circulating the water from the process to the cooling tower. So we will be just giving as an energy conservation measure, which we call it ECM. We will just say you can switch off one pump and you can run with one circulating pump, for which your flow is sufficient and you can achieve the savings. So next one will be the furnace. in a typical automobile plant, so automobiles are also an energy intensive sector. In automobile, we have a large portion of thermal energy. If you see, 71% you are using thermal energy, and only around 30% you are using electrical energy. So these furnaces use LPG and sometimes natural gas, petroleum gas or natural gas like CNG or LPG, and this contributes to the larger part of automobile industry. Automobile industries, they will use aluminiums and other alloys so that they can make spare parts out of it. So these spare parts consume more energy. So these are the crucibles. I think this is the die casting furnaces, which is you can see the thermal image next to their actual image. So if you see the thermal image, it is in open condition. Then the first thermal image, it is around 500 degrees on top of the crucible, and the next image, if you see, it is around 400 degrees. So if you keep that lid open, 400 degrees of heat is always emitted to the ambient, and there is no preventing, or there is no usage of the heat. You are just increasing the metal temperature, you are melting it, and you are having it in a crucible, and you are just emitting it into the atmosphere. So unless and until you are going to use that into a mold or use that into a die cast, then you are preparing a spare part. Till then you will have this in the crucible and your energy is being wasted. So this kind of energy loss is also happening inside this automobile plants. So this is also a holding furnace. So holding is just that crucibles, one large crucible will be there, and you will have separate die casting machines. So if you have to transfer this one large molten metal from here to other single die casting machines, you will just transfer it to a holding furnace. So the holding furnace, its function is just to maintain the temperature and just keep the metal in a molten state. So when the time comes, it will use the metal and it will produce the spares. So this holding furnace also has the open lid, and there is energy loss on this also. And one more thing which was observed is this crucibles, when you use it for a longer period of time, you will have a layer formed over inside the crucibles, and the layer is not just a simple thing. So if you see day in and day out, 24 hours these plants will be operating, and if when you are adding more metal and you are going to heat it using LPG or CNG, so each kg of gas is precious. So instead of using 1 kg of gas to melt the certain amount of material, you will be using 2 kgs or 3 kgs of gas, just because your layer, the inside crucible layer is having some slag or some kind of unwanted material. So these things will increase your energy consumption. So these are the specific energy consumption values which we had arrived in the plant. So if you see on the y-axis, it is in cubic meters, standard cubic meters per ton of metal. So for 1 ton of metal, how much standard cubic meters of gas is required? So if you see in each furnaces, you will have 64 cubic meters of gas and 80 cubic meters of gas, etc. So this is the heat loss. Just because of the heat loss, when it is not covered properly, or since it is not atomized, there are also other atomized plants which have a lid closed conditions, and whenever necessary, this molten metal is used for die casting. So these alternative measures are also there, but still industries are opting for open lid, and they are using it as melting furnaces, and they are transferring it to holding, then they are having it in open condition itself. So because of this, the loss around 2 lakh 20,000 cubic meters of gas per annum will be there, just because of this radiation losses. So next one will be the transformer. This utility is found, this is not just an utility, it is found in any place or any household or any building in that case. So you need receiving, whatever facility is receiving power from the substation, you need a transformer for that. So this, in simple terms, if I want to say, the demand management is done like, let's say in a household you have one TV, one fridge and one AC, and now you are adding one more AC, so your demand just got up. So your demand, like initially you needed 2 kilowatts, now you needed 5 kilowatts, just because you added one more air conditioner. So this applies to the industry also. If you are adding more machineries, your demand increases. So demand comes at a cost. If you are going for 10 kVA of demand, you need to pay certain cost to the TNEB, and if you are going for 20 kVA of demand, you need to pay a certain cost, and this is a fixed cost. So this cost is varying, and this cost needs to be addressed in your electricity bill. So unlike us, like household or simple consumers, like in an industry there will be in lakhs and crores. So annually some industries will be paying crores in amount just to the electricity TNEB. So these people need to focus on their demand also. So these are other few technicalities of the transformer, like energy, power factor, harmonics, and other things we will be observing in a transformer to quantify the losses in the transformer. So this is a simple textile process flow. So you will be sourcing the raw material, and fibers will be prepared from that. So, and you will spin the raw material into yarns, and the yarns is sent for knitting and wet processing, and finally you will be giving it to the garments. So here the spinning and wet processing, so these things till wet processing you will have an energy intensive sector, since you will have spinning machineries and you will have for wet processing also. So these kind of machineries will consume more energy. Okay, they will be disposing, that will be as a second quality cotton or second quality fiber. They will remove it, and they will just first quality will be sent to the processing, and the second quality is given for some other purposes. I'm not sure about the applications such, but it is not used in the process. They will not be reused again in the industry. It will be sent again outside. So then we can uh, so this is the energy split up of the unit in a typical spinning unit. So here we see the third part is the spinning. So this spinning is using compressors, and you are having the second part. If you see the right hand side of the energy balance, you see compressors, you have HF plants and humidification plants, which I had mentioned, and the next one is the AWS, which is the automatic waste evacuation. Then you have carding, then you have spinning, which is consuming around 50% of the energy. Then you have transmission and distribution losses, then preparatory. So these are the energy split up of this utility. And if you see on the left hand side, what are all the energy sources which this textile spinning unit is using. So it is solar for 40%, wind adjustment for 40%. If you observe in Coimbatore or some other textile sectors, most of them are using wind energy. So wind energy is a prominent consumer. Wind energy consumption is prominent in regions of Coimbatore and textile sectors. And also you have solar panels, and from the grid you have 14%, and DG is present in almost every industry, since due to blackouts and other such situations you will have diesel generators, just to have the process fault free, and you can continue the next level of processes. You will have DGs. So this is a typical AWS setup, which is automatic waste evacuation. Initially, when the raw material cotton is coming in, so how the waste is evacuated, you will have blowers and you will just suck the waste out of it. So here one simple measure which we had observed, this was the in automatic waste evacuation you will have just one blower, and that one blower sucks the waste from all other individual machines. So in the last machine, if you observe, it is around, the requirement is around 750 pascals. The 750 pascals is the required amount of pressure, but the blower is generating around 1250 pascals. So this gap is what we are addressing. So the 890 pascals which is present in the last machine, 7th machine, is just enough to keep the process running, but we will be producing 1250 pascals of pressure. So this kind of mismatch is very simple, and it can be noticed by many of the things are since people will be focused more on the process and how to keep it proper, this energy aspect needs to be focused. So these are a few examples of how this pressure value is increased. This 1250 is just because of these minor breakages and minor air which is infiltration is happening in the suction lines. So because of that, your energy consumption is increasing. So since if you need more pressure, you need more energy to produce the same amount of suction. So this is the generation side from the energy from the AWS. Here you will have large fan blades, rotors, which will be rotating inside this, and the suction is created from this point. So these are all the, so I had mentioned 7 machines here. So 1, 2, 7 you will have there, 1, 2, 3. So these machines will have the pulleys which is mentioned here. So these pulleys are also using motors. Motors will be used, pulleys will be used for the motor, and this pulley will be driving the motors. So this one way of conserving energy is to use variable frequency drives. These variable frequency drives, you can use any pulley to do your operation, but this variable frequency drive just will provide you the right amount of torque and right amount of speed so that it can produce the necessary amount of energy. So this is the example of from the generation side, you are producing 1150 pascals. So if you reduce it to 1050 pascals, the energy savings corresponding to that will be 58.5 kilowatt is used initially, but after the changing VFD, using the from normal motor to a VFD motor, you're going to 53 kilowatts. So this is translating into your energy conservation. So instead of using VFDs is like you need to invest for the motor, you need to buy a VFD, you need to install a VFD, you need to wire it. Instead of that, if you have one more option, you can change the pulley diameter of the motor, so that your necessary torque is like, the torque required is like only around 10 Newton meter, and you'll be producing only 10 Newton meter. Based on that, you will add a pulley for that. So when you do that, your power consumption is coming from around 12 kilowatt. 11.97 is 12 kilowatt, is coming around 8.5 kilowatt just by changing the pulley of your motor. So these are few boiler measures. So due to time constraint, I will just explain what are all the measures and we can move on. So currently in boilers, installing economizer or air preheater, you can improve your efficiency, you can improve your waste heat recovery, and you can also improve your fuel, you can reduce your fuel consumption. So based on installing economizer, these are all the savings which we had proposed. And also, main part is like you are just providing water to a boiler and it is converted into steam. So when the water you are providing it in an ambient temperature, instead of that, if you preheat it using the boiler's waste heat, so it will improve your boiler efficiency overall. So these kind of measures are also we will be providing for the industries. So these measures can be done by SOPT, which we call it as steam operated pumping traps, and also PPPU pump, which is pressure power packaged unit. So these two are just whatever condensate or whatever hot water which you obtain from the process after the steam is utilized. So you will utilize the heat and you will reheat the feed water. So when you reheat the feed water, your fuel consumption comes down. So you don't need to take it to a temperature where it is already heated. So as a classic example of air leakage, here it is a steam leakage. So steam is also under high pressure. So these steams are also will be trying to escape, and some places your steam is leaking. So these steam leaks alone contributes to around 4 lakhs of monetary savings, and around 100 tons of fuel can be saved just by arresting these steam leakages. So this is one of the technologies which we had suggested in CIP. CIP, as I had mentioned, in pharmas, in dairies. So wherever you need food grade products, so these areas should be sanitized and kept very clean. So when the milk is pasteurized, the whole pasteurized utilities should be cleaned and it should be maintained in such a state so that the next batch of milk is arriving in, so it doesn't contaminate the next batch of milk. So for that cleaning process is the industries use CIP, which is cleaning in place, and this cleaning in place will use hot water and it will use caustic soda. And caustic soda is not the direct caustic soda which we know, that is there is a type of caustic soda which is especially for this, and they will rinse the whatever is present inside the pasteurization chambers, and they will keep it ready for the next batch. So whatever hot water and whatever caustic which is used on a daily basis. As I said, milk industry is like energy intensive and being used daily, like 24 hours operation will be there. So this hot water and this caustic can be reused again, and this energy in the hot water and the caustic, so how much amount is needed can be used, and whatever hot water is coming out of it, usually it is discarded. Instead of discarding it, you are using the heat from the hot water and you are using the caustic which was present in the effluent, and you are reusing it again. So based on this, so there are many articles and papers which is proposing this. So this also improves your overall boiler condition. So just you can see the correlation. So if you just change a simple system in your CIP, your overall boiler fuel consumption is reduced. So if you are using heat from the hot water, so you don't need to produce that heat. So you are just cutting one by one in many places, in various places. So this is one of the case studies for chillers. In chillers, major in chillers is that the optimal water flow rate should be there. So in chillers we are just taking one fluid and taking another fluid, it will cross each other so that heat exchange takes place. So the rate of flow at which flowing should be in an ideal value so that in a proper manner. So this flow rate is this flow rate should be optimal if the flow heat energy transfer is not happening properly. Calculated, and if it is beyond the limit or if it is value, we will be providing this measure saying that your flow rate is not optimal. So finally this implementation. So here we will have after post whatever measurements we did, whatever conservation measures we have given, so they need to follow it. So if they are not following it, so these conservations are not fruitful. So for that purpose, this implementation is done by the IoT. So in IoT and energy audit tool also we are doing. So the data is monitored live. So we will just take all the parameters which is necessary for us, and we'll be monitoring it from a place, distant remote place. And also if any changes are occurring in the values, we will report to the industry. So this is after post implementation also. So this is our website. Thank you for your patience and thank you for your time. So I'll conclude my speech. Thank you.